Hello, everyone. This is Larry Sampson, and welcome to our 6th or 7th, I don't even know which one it is, session of Lunch with Larry. So we're going to have a fun discussion today about system simulation, and I think I'd figured this out by now. Sorry about that. Okay, so today we're going to talk about system simulation, and it's a terrific discussion that we're going to have. We're going to progress into system simulation from our discussion last time, which was model-based systems engineering, and have a bridge discussion into how do we take that model that we developed in model-based systems engineering and use it to drive our system simulation activities. So just go ahead and start the discussion with a little bit, just as a reminder, if you want any contact information, we're thrilled to talk to you about any of these topics. And this is just the slide that I use to give you all my contact information, LinkedIn, phone number, email address, and of course our scan QR code for registration with this particular webinar series. And at the end here, we're going to have the next webinar series, which is going to be related to manufacturing. So look forward to talking to you about that. That's just a little bit about me. I just wanted to mention all of this work that we're doing, we're building out in the context of an open source ventilator project. And so yes, last week we talked about model-based systems engineering and the model that we use to build out our ventilator, like what does the performance need to be. And again, we're going to take that in the ventilator discussion, and we're going to progress that now into system simulation. So just a little bit of a note about the fact that the data set that we're using is this open ventilator project. Just as a reminder, the value that we're really talking about in design excellence, we have 3 different values that we talk about. In this case, we're really talking about the first one, which is really productivity. What are world-class design tools? How do those design tools, how are they used? How do they relate to one another? And how are they represented in the digital thread? So first thing, and what this session is really about, is this productivity. In addition to that, though, as we talk about design excellence in these different topics, we're going to get into other things too. Speed, which is really integration of these design tools. ECAD, MCAD is one really good example of that, how we progress electronics designs and use those electronics designs in the mechanical CAD models to allow us to do other kinds of product simulation, just as an example. And then finally, complexity management. How do we put all these files together, millions of different files, you know, in different data sources? How are they related to one another, and how do we run those through change management? So those are the 3 different values, just to give you a preview. And of course, the result of that, what we really want out of this is design innovation. And so that's really the setup. And what we're going to do now is we're going to talk to our expert witnesses here. We have 2 folks we're going to talk to, Alex Francois Saint-Cyr. Hopefully I'm saying that at least partially with a good French accent. Alex is our portfolio simulation expert, and really she goes across the portfolio of all the different simulation tools, and she'll give you a background here just in 2 secs. And then Bob Ranston, and hopefully I got that right too, is system simulation evangelist. So he's really our AIM-Sim modeling expert. He's an expert in this particular tool used to do system simulation. So Alex, maybe you can just provide a little background as we move into the discussion here, if you don't mind.
Sure, Larry. As part of Flumerics, Mentor Graphics, and now Siemens Digital Industry Software, I've been deeply involved, with helping customers adopt simulation across multiple industries for over 20 years. I've also had the opportunity to manage an engineering team that was very passionate about simulation. So I'm really thrilled to be able to talk about system simulation with you today.
That's fantastic. So Bob, maybe you could provide a little bit of a background.
Yeah, thanks, Larry. My name is Bob Ranston, and I've been working with system simulation for about 15 years, 12 years with Siemens and predecessors, focusing on our behavioral modeling in a variety of different industries, basically physical system modeling, behavioral modeling within our SimCenter AIM-Sim platform.
Well, that sounds good. I knew I'd get your last name wrong. So Alex, maybe you can start us out by providing an explanation really of why system simulations brings together or contextualizes the systems modeling or model-based systems engineering work.
Sure, Larry. To answer your question, let's quickly review the results of the survey that we ran at the end of last week's session. So the first question was about people's experience with integrating the different subsystems that make up a product. Well, it doesn't seem that things are as smooth as butter, for most of our audience. In fact, you can see that the main challenges are to be able to satisfy all the requirements, and also the fact that each subsystems team tends to be siloed, which really leads in this case to many unexpected integration issues. So your session last week really illustrated how a model-based systems engineering approach can help address these issues. Today, we will focus on the overall system performance aspect, which is where system simulation comes into the picture. So the second question of the survey, let's see if I can get it to show here. There we go. So the second question of the survey highlighted that the vast majority of our audience from last week was not familiar with mechatronic system simulation. So what is mechatronic system simulation, and why does it matter for product development? Well, let's first define what a mechatronic system is. A mechatronic system is a system that requires the combination of mechanical, electrical, controls, and software subsystems or components to function. So what system simulation allows you to do very early on in the design cycle, when 3D CAD geometry has not even been generated yet, is to create a virtual model of the mechatronic system and analyze its behavior across multiple use cases. So as such, it provides insights on the overall system performance. And with the analysis running within minutes, you can quickly balance all of the medical device's attributes, reduce compliance risk, and test your controls loops before any prototype is built so that minimal adjustments are made during the experimental phase. So let's go ahead and revisit, our ventilator example from last week to illustrate how system simulation can be used. Well, if you look at the systems diagrams that Tony showed last week, it provided some insights on the main ventilator functions, as well as its connection to the patient and also to the patient caregivers. Let's now consider the ventilator from a mechatronic system perspective. It contains electrical components such as the power supply and a motor, that would spin the air turbine. It also requires mechanical parts such as the fan to make sure that these electronics components do not overheat. The air and oxygen flows are regulated with valves and sensors, so there's no to be able to make sure that those will be controlled appropriately. Then you have a microcontroller as well, which will allow to control oxygen and airflow levels. So all of these component characteristics will have to be taken into account in the system simulation model to assess the performance of the ventilator. There's an even more critical component that I would put in quotation mark here, to consider in our system model, and that is, of course, the patient. So the system model must also simulate the breathing behavior of the patient, and therefore must include data such as lung volume and lung stiffness.
Okay, so maybe, Bob, we could move over to you and we can have you run us through. Give me a second here. I'm going to move you to your model. If you wouldn't mind, maybe you could run us through the AIMSIM model and show us how the system model is represented by the system simulation.
Yes, thanks, Larry. Yeah. Let me start with kind of a very, very quick idea of what SimCenter AIMSIM is. And so it's a system simulation platform to model behavior of systems. And the way we can do that is we have a long list of libraries that are based on different types of physics, and each library has a set of components. And so for here, for example, I can define what gas I'm using to flow through my system. I can give a pressure as a boundary condition. Then I can start like, okay, I have a certain orifice as a pressure drop. Then I have pipes, or I have a compressor, and connect the whole system up together like that. Then I can set the behavior of the different components with some basic parameters like pipe diameter, length, and some pressure drop characteristic, and simulate the dynamic behavior of this model. So what I did for the ventilator, let me close this model and go back to the model that I had, is I built up such a system. And on the top left, you can see how I defined my mixture of gases. So we have nitrogen, oxygen, carbon dioxide, some water vapor. In my mixture, water vapor can actually condense, so I can track the humidity levels. And on the center top, I have a controller. And this controller, in this case, is quite basic. It's controlling like the airflow control valve to maintain a certain pressure, for example. It's opening up the inspiration and expiration valves and closing them. So this controller could be like replaced with the actual C code of the controller or a Simulink model that we may have, for example. But to model the physics, we're using SimCenter AimSim. So the ventilator unit is described with like an air inlet and oxygen inlet. I have a compressor that's pressurizing my air, and some other valve like an on-return valve, a pressure reducer, and an airflow control valve that's actively controlled. And some pressure relief valve, and there's some sensor in there. Then I have a humidifier that can typically be part of the ventilator unit, and it can also be a heater that will heat up the air. I can have some sensors, and then that is my system. But then on the right side, I have actually my patient here. And the patient lung is kind of a custom component. I can look underneath to see what that represents. And I have a lung volume and a lung compliance that I'm modeling, and functionally I have some oxygen exchange for CO2. I have an airway resistance modeled as well with some typical parameters. So what I can do now with this model is I can compile that into like a simulation executable. Okay. And then once it is compiled, I can run the simulation. And if you can see, if I click run here now, it's starting to run, and it runs pretty fast. So I'm running it, if I do a 1 minute, 60-second simulation, which runs in about 10-15 seconds. Okay. And then what I can look at, and clicking on my lung, I can look on the right side here. I can see some parameters that I've had predefined, bit of a lung volume, lung stiffness, and then I can see some results. So I can look at what is the pressure inside my lung. You can see it cycling up and down. What is my lung volume here? And then more importantly here, what's the oxygen fraction inside my lung? Okay, and you can see that even though my air that's coming in has like a 20%, 21% oxygen concentration inside the lung, because I'm doing the exchange, the actual oxygen concentration goes down. And in this case, I have my oxygen valve closed. So what I can do with AimSim, I have a study manager here where I can put in the oxygen valve opening position and create a study. In this case, I set up a study where I am having like 3, I'm having it closed, and then 2 other sets where I have it open. So I can actually do those 3 runs, and they're actually running in parallel now, and to see what the impact is on the oxygen concentration inside the lung as function of the different oxygen control valves positions. So once that's done, I can actually change this plot. You can see here the impact of the valve opening on the mean oxygen concentration inside the lung. And this helps.
You can imagine that the
control.
Sure, the validation of this model would allow you, if you did the validation work against this model, now what you could start to do is use this model as part of your development activities and making changes to the story. And one of the things in the story we've been developing, we were talking about using this ventilator on more than one patient. So how would we go about looking at the viability of the change? So if we said we want to now put this ventilator on 2 patients, how could we work that into this model?
So that's actually very straightforward to do. I can go back to my sketch mode here, and the ventilator unit, humidifier, etc., remains the same. And I can basically say from the inspiration or expiration, maybe you have the same cycle, but from there on, this whole patient, including the tubing going in and going out, is duplicated. Right? So I just have a second patient in here. I would have to add some nodes to basically bring this here, and then have another expiration valve connection there, which I've done in my second model here. So in this second model, I've set it up just what I did. I duplicated the lung and have patient A and patient B. And then what I can look at is like doing a run here and look at a plots here, for example. So I can then look at the volume, flow rates, and the oxygen fraction, and I can go back and compare that to, we go back to this, undo this here, come back to this model, and can compare that with what happened with one patient. And what I will see, this is compiled, I can look at my volume, the lung volume on this run. And I can zoom in a little bit. So the blue line, I can change the color here to orange, so it is a little bit of visible. I can zoom in on a specific cycle here. But you can see that by the total volume change inside the lung, of course, is lower with two patients than with one patient. But by how much? It's not half, because just the way the system works, it's not half, but it's about 20% lower or something like that. And then I can make changes to my system to allow for a longer inspiration cycle or higher like pressure inlets, etc., to make sure that each patient gets enough volume.
Yeah, one of the questions that you'd want to handle with is, you know, we want to have a variety of different variables like tubing length, lung volumes, and stiffness. Maybe what we want to do is have one patient be pediatric and another patient be an adult male, and the differences between those. So how would we go about using this model to sort of investigate the different variables that might be, you know, considered?
Yeah, so here, if you look at each patient component, and we have a set of parameters like lung volume, lung stiffness, some airway diameter, length, and then resistance. And for the tubing, I have a certain length and diameter. I can change that for one of the patients, for example, say, okay, my lung volume is 20% bigger, and my stiffness is 20% smaller, for example. And then I can rerun the simulation and see what the impact is of having a different lung. And I have actually set that up already and did the simulation and saved that as an experiment here with an AIMSIM. So I can right click here, apply the parameters, and load those results. So now I can open up the same plot that I had. And you can see now that, okay, I had, my patient had a higher, 20% higher lung capacity or lung volume. So you can see the breathing in, breathing out is the same, but there's an offset just because of the total lung volume. You can see that the flow rates through the lungs in the middle sketch, it's very similar, but they are a little different. And on the bottom, you can see that there's a different oxygen fraction, an average oxygen fraction inside the lung. So the two patients, that are on the same ventilator, they each get a different oxygen concentration at this point. And what we can do now is further that down and look at how do we control the inspiration expiration valve? Do we need to add separate valves to go to patient A and patient B to ensure that they get the same or the right amount of volume and oxygen in the system? Okay.
Yeah, that's terrific. So if we, you know, so we build this model, we validate the model, and we're confident that we get the results out are what we would expect to see in a patient. Maybe you could talk a little bit about how to make this model more accessible to the physician. So they don't have to get into this, the complexity of this to do this evaluation. Maybe there's a more limited set we could make available to a physician. Maybe you can help us with that.
Yeah, so we have our web server, SimCenter web app server that is basically web-based. So I just loaded my browser and I'm logging in. And I have uploaded that model to the web app server. And the web app server allows me to customize what people will see, what the end user will see. They can launch this from like their tablet, their phone, or the laptop, and look at what models are available, for example. So in this case, I have this one model, the ventilator analysis, uploaded here, and they can create a new project from that model. And then they can see what parameters I have allowed them to see and make changes to. So patient A, patient B, there's some other parameters. So patient B had like a larger lung volume. So let me make that 4, a little lower stiffness. And let's say, okay, the tubing length to the patient is twice as long as patient A. And then they can click simulate, and it will apply these parameters. It will prepare the simulation. And then in the background, it will actually execute the simulation. See, it is running, and it may take 20 seconds for it to run. But then there's another tab that once the simulation is done, those results that are analyzed here, that are simulated, are available to the physician or the nurse or whoever would be right there and needs to make like some setting choices based on these parameters. So you can look at the patient A oxygen fraction, compare that with patient B oxygen fraction, for example. And you can see that in this case, there's maybe a 5%, 4% difference in oxygen concentration between the patients.
That's fantastic. So, and maybe if you don't mind, Alex, I've got a little question here. How is it that we would, I know we have testing as part of our portfolio, but in this case, we have these models built out. It seems to me that validation of these models might become a really interesting part of the work. In other words, so we have the variables and we are making assumptions, but a lot of testing that goes into this. Any comment that you might have on how to validate a model like this? So this is an extemporaneous question, so hopefully you can answer it.
Yeah, no, Larry, I think it brings like an important point, which is the fact that system simulation is really good to be able to be used early on in the design, like you know we've been talking about here, but as more data becomes available, even like with 3D data, for instance, on the CAD side, you can also refine some of those components, because some of those components might be very complex and may require more like 3D type of simulation to be validated. So that would be one way to do it. Or, you know, like you said, you know, testing, you know, for some of those components could be done as well, so that you can really fine tune this system simulation model and have it really has your digital twin, you know, of the product performance as a reference moving forward.
Well, maybe what you could do is talk through and maybe provide us of an example of how the tool was used to assess the performance of a respiratory device. I gotta click on all the right things. Maybe you could help us understand how to, you know, how we've done this in the past, assessing the performance of a respiratory device.
Absolutely, Larry. So Dräger Medical is a German manufacturer of medical equipment, such as breathing and anesthesia products. And as they were looking at developing a new anesthesia machine, they turned to system simulation very early on in the product design to determine the precise dosage of anesthetic agent that would be required for a variety of ventilation and breathing support conditions. So, you know, in this case, system simulation not only allowed them to size the different system components, such as like the piston, hoses, heaters, and valves, but it also provided them the opportunity to test the control algorithms, for the ventilation and the gas mixing before any prototype, was built. So as such, Draeger could quickly understand what the appropriate gas mixture should be based on the different patient-specific breathing behaviors. There might be some normal breathing, or there might be some emergency breathing. All of these aspects, you'll be able to test very quickly using this model. And therefore, this virtual model of the anesthesia machine really became the digital twin representation of the real product performance for Draeger.
Sure. And I got a couple of questions coming in too. Maybe Bob, you could take this one. The question is, are the physics models of the pneumatic components able to model the compressibility and inertia of the gases? I don't know if you have an answer to that one.
Yeah, definitely. All the volumes and components in the AIM-Sim, they have either a combination of resistance and compressibility as well as inertia effects. So you can look at dynamic transients.
Fantastic. And Alex, I'll give you this one. How would someone get access to the web app server?
Well, what happens with the web app server is that it's an interface that is linked to MSIM, in the sense that you can develop an MSIM model, and that becomes then, the MSIM model then becomes almost like a library that can be used then, from the web app server by anyone, having access to a tablet or computer or web server, so a web browser.
Sure. Okay, that's it for the questions. I'm going to go ahead and end the session, but I just want to get, if you're interested in this product and kind of the model that's been built out around the ventilator, we'd be more than happy to talk to you about that. So feel free to get back with us either through my email, or happy to have sales get back with you as well if you're interested in a further discussion. Probably offer having Bob and a session with you to talk about specifics about your particular application. We'd be happy to do that with you. So this slide really talks about this particular webinar series. The next one's going to be electrical engineering. We're going to have Ralph Palmer in and talk about schematics and building those into PCB designs. And so that's next week. And then I just wanted to also put up our next series is going to be operational excellence. So we're going to talk about how to transfer these designs into production, just to take a break from design for a month, and then we're going to come back to design. But operational excellence, we'll talk about manufacturing process planning, manufacturing simulation, and manufacturing execution. So we're going to take this model and all this work that we're building up in the design and start to progress that down into the manufacturing processes. So I'd just like to say thank you so much for coming, spending your half an hour lunch with us, and sure look forward to you meeting with us in the next session. So thanks so much. Take care.